The 80% waste. Modern large language models are wasting 80% of their parameters on static weights that serve as nothing more than rigid lookup tables. This inefficiency stems from the multi-layer perceptron, an architecture we have used since the 1980s without fundamental structural changes. Kolmogorov-Arnold Networks, or KANS, have finally broken this cycle by moving the learning process from the nodes to the edges. By shifting the mathematical burden, these networks can match the performance of traditional models with a fraction of the hardware footprint. And the mechanical reason for this reduction is found in the way these networks handle nonlinear data. Learnable splines replace fixed weights. To understand why KANS scale differently, you have to look at the edge weights. In a standard MLP, a node sums inputs and passes them through a fixed activation function like rel_u. KANS replace those fixed nodes with learnable splines on every single connection. Instead of a single number, each edge is a flexible curve that adapts to the data. This allows a KN with only 200 parameters to outperform an MLP with 2,000 in complex function approximation tasks. This shift effectively eliminates the need for massive layers just to capture simple nonlinearities. This flexibility is what finally cracks the long-standing problem of model transparency. Ending the black box era. KANS solved the black box problem by being mathematically transparent in a way that transformers are not. Because the edge functions are univariate, we can use symbolic regression to convert a trained network into a clean mathematical formula. Researchers at MIT recently used this to rediscover physical laws from raw data without any human guidance. It turns out that when the model is forced to learn functions rather than weights, the underlying logic becomes human-readable. We are no longer guessing what happens in the hidden layers because the functions are the layers. But this mathematical elegance comes with a significant trade-off in raw speed: the high cost of complexity. The training overhead remains the primary barrier to total adoption. While KANS use fewer parameters, the computational cost per parameter is significantly higher because calculating B-splines is more intensive than simple matrix multiplication. Current benchmarks show that while a KN is 10 times smaller for the same accuracy, it often takes 3 times longer to train on existing hardware. We are essentially trading parameter count for architectural complexity, which challenges the brute force scaling laws we have relied on for the last decade. This bottleneck means the transition to function-based networks requires a complete rethink of our current hardware acceleration strategies. The signal under the noise. The emergence of Kolmogorov-Arnold networks signals that the era of massive, inefficient dense layers is nearing its technical limit. By looking at the performance of KANS in recent physics-informed neural networks and high-precision engineering models, we see that the real value is not just in being smaller, but in the shift from curve fitting to function discovery. This structural change addresses the core inefficiencies of the MLP mentioned earlier and provides the interpretability we have lacked since the first transformers. For developers and engineers, this means the next phase of optimization will not be about finding more GPUs, but about redesigning the fundamental math of the network edges. If you are building for 2027, you should be tracking the integration of KAN layers into hybrid transformer architectures. The first production-ready kernels for these splines are dropping next month, and that is the specific signal to watch for real-world performance gains. Subscribe for more.